Welcome to solverfy.
Okay, so for this problem, you have two wires and they have current in opposite directions. They have they're given the problem gives you the separation between the centers of the wires and yeah, I guess I already said the radius of the wires. You can neglect the flux within the wires, but you want to consider the flux between the wires and get the inductance per length of the wires. So I'll go ahead and draw this out. Um, So I think the approach that I want to use, well, actually, I know the approach that I want to use is finding L through using the formula L is equal to phi times N divided by the current. And we can get the flux, we want to get the flux through this area. Since the magnetic field due to the wires is varying, we have to integrate over um, the full area to get the proper flux. If it were constant, it would be much easier. The currents are going opposite ways, so if you use a right-hand rule, you'll get that the magnetic field is going from each wire is adding, it's not canceling. And so, yeah, so you'll end up doubling, or excuse me, so yeah, they add together, I guess is all I was trying to say. And so you want to add the contributions from the fields. So first, let's get the flux. So flux is going to be, again, the integral of b dot dA. And then dA is going to be, let's call that x and let's call that y. So we're going to integrate dA is going to be dx times dy. And then the b is going to be the field due to the two wires. And the field due to a wire is mu naught I over 2 pi r, where r is the distance from the wire's center. So you want to integrate the, let's say, actually, let's call the distance from this wire r, and then so you have like the first wire, you're gonna have a term 1 over, oh, and then the r dimension is going to be the x dimension. And so you have a 1 over x. And then the other one is going to have this distance between them minus x, because we ultimately want to get this distance for that term. So we'll add plus 1 over, and I'll call this d, plus 1 over d minus x. And for the bounds of our integral, we want to start, since we're not including the flux from the wire, we want to start at the radius of the wire. So, and that's 1.53 millimeters. So I'm just going to actually use numbers here. Sometimes I like to do that rather than create new variables. So we want to start integrating here, and then we want to end the integration one radius away from the separation. So we're ending it just at the border of this wire. So it's going to be this d minus 1.53 times 10 to the minus 3 meters. And we'll integrate that with respect to x. And so I'm just going to say I just plug this into a calculator, an online calculator, and I'm guessing you can probably do these integrals without too much help from these videos. So I'm just going to say plug this into a calculator, and then you'll get an equation for phi. And of course, it'll depend on, oh yeah, oops, sorry, actually, let me back up a little bit. So I said we're going to integrate dx dy. So that's the dx part. And then we also want to integrate along this length to get the flux. So we can call this length some kind of L. And then the integral of this dy is just going to go from 0 to L. So it'll just give us a factor of L. And so basically when I did that, I got a number times L. And do they actually give you the currents in these? Let me double check. Oh, okay. And so you're not given the current, so you can't really come up with a number either. That's okay because for our goal is to get L per unit length. And so we'll divide out that L. And so we just need to evaluate this. N is equal to 1. And then, yeah, there's only kind of like one surface that's receiving flux. So this N goes to 1. We're dividing out this I. We're dividing out this L. And then when we do that, I got that L per unit length was 1 point. Let me go look at my calculations. Yeah, 1.8081 times 10 to the minus 6 henries per meter